So today I'm going to tell about the twist fields. The idea is the following. For example, let's remember this Bosonization. So we had formulas like this. There is phi star of z, which is written as I phi phi minus e to the I phi plus e to q z to a0. And there is psi of z, which is e to minus I phi minus e to minus I phi plus e to minus q z to minus a0. So the question is, what is the global behavior of psi? So we see that if a0 is not a integer, then psi star of z behaves. So let us say that this a0 acting on the highest. No. So a0 acting on vacuum. A0 acting on vacuum. Let us denote this vacuum sigma. No. Vacuum is non-integer. So let us say that a0 acting on vacuum is some sigma, which is some complex number in principle. So in this case, this psi star of z behaves like z to power sigma, and at times some series. As before, over half integer numbers. Psi p over psi star p over z p plus 1/2, and in the same way, psi of z behaves like z to minus sigma. Sum of p so they have an interval monodromy around 0. But we remember that there exists inverse formula for Bosonization, which expresses our current J of z is as psi as a regular product psi star of z, psi of z. And now there are several important things. So the first thing is that OPs of operators do not depend on their global behavior. And the second point is that if something is if mm, if all operators are used using OP, so let us call that the sigma is called twist. So, and this is so because every OP can be so any computation with the OPs can be um, done only in terms of this operator algebra. We don't need to study the mode structure of this operator. So if we see that some operators form from ionic algebra locally, then if we construct some current from these operators, then it will still be the current. It will have the same OP with itself. So on the third point is that this way we get the same algebra for any twist. So, and in this particular example, what does it mean? So, so we say that G of Z equals to this product psi star of Z psi of Z. In principle, we can do the same for this UK generators. So, yeah, this kind of n equals to 1. If we have arbitrary n, we can have sigma 1 and so on, sigma n, and we can construct UKs of Z, which are regular products of psi star of Z, d k minus 1, psi of Z. So, so is it fine? And the question is, what is the precise answer? So, if you construct G in such a way, so we know that OP of psi itself, psi of W, equals to 1 over Z minus W. So this is subpoint, and then it means that OP of G of Z with G of W equals to 1 over Z minus W squared. Because this computation does not care about the does not care about the global behavior of this field. So we can compute now what is the explicit expression for this current. So this psi star alpha psi star of Z psi of W, if you write it more explicitly, it equals to what? It is a product of some standard fermions with integer mode expansion times Z to sigma and Z minus sigma. And so it can be written like Z to power sigma W, so psi of W, W to minus sigma. And it is 1 over Z minus W plus normal ordering of how to, maybe better to write it like this. Plus usual fermionic normal ordering psi star of Z psi of W. So it is clear. So and now we need to express we need to expand this around the second point. So it is Z to so we need to expand this around point W. So it is Z to power sigma, no, W to power sigma plus sigma W minus Z, oh, Z minus W, or W plus and so on. One over Z minus W. So W to power sigma, W to minus sigma. Plus this normal ordering. So here we need to take to keep two terms. One term is 1 over Z minus W. Another term is this one, which is constant, plus sigma over W, plus normal order of psi star of W, psi of W, plus something of order Z minus W. And from the other side, we see that it is a sum of ANs over W So it is j of w, which is sum over n wn plus 1. So ans for n different than 1 are just standard, like equal to sum over psi star n psi p minus n. We don't need to normal order them. Psi star p, no, p n minus p. And A0 equals to sigma plus sum over p normally ordered psi star p psi minus p. So is it clear why these operators form the same algebra as for sigma equals to 0?
So the dependence on z plus equality, but with one over z minus w plus
Oh, yes, thank you, thank you. Yes, plus regular, plus all of z minus w. So this j, so this is precisely what is the meaning of this definition of normal product. So it can differ from the modes normal ordering when some modes go to the left, some to the right by such kind of terms. So here there is this explicit dependence on sigma, and it is clear that such operators like a, k, a, n, maybe let's write like aka minus k equals to k. And so in particular, a0 with all k's is 0. And if we add some constant to this a0, it is more or less trivial that algebra does not change. So in this way, we can obtain a realization of this Heisenberg algebra with arbitrary a0 on the space of free fermions. Which is not obvious from the beginning, because here so if we think only about complex fermions, about true complex fermions without any twists, then we can expect representations of this current algebra only with integer sigmas. But in reality, we can get arbitrary number by such modification. So we can also try to do the same for this UK generator. So let us consider. Fine. So let us consider now psi star of z d k minus 1 psi of z. So it equals to what? It is d k minus 1 z to sigma w to minus sigma over z minus w, and this is derivative in so this is derivative in w. Wait, actually I thought that there is some better way to do this. Let us better consider such generators with derivatives acting on the first part, psi of z. Dk minus 1. So it is z to sigma, w to minus sigma, z minus w, plus normal ordering. Dk minus 1, sum psi p plus p over z p plus 1/2 z to sigma psi q over wq plus 1/2. So you see, when we compute this k derivatives of a series that contains z to sigma, the sigma will explicitly appear in the expressions. But we can keep it as a single object, like normal order product of fermions, and look at the first term. So this first term looks like d that k minus 1/2, k minus 1, and here we expand on this the power series. So it is z minus w 1 plus sigma over z plus sigma squared over z plus sigma plus 1 over 2 z squared plus and so on plus sigma plus 1 sigma plus n minus 1 over z so we need to expand it until k factorial zk z minus w plus this normal order. And I forgot powers of z minus w. So So all these terms are killed by this derivative, and so except for the first one. So it is dz k minus 1 over, oh, we can write what it is. It is some k, probably k minus 1 factorial, maybe minus 1 to power k. No, plus 1. So then the next term is uh, is 1 over k sigma plus 1, so 1 sigma plus k minus 1 1 over w k's plus this normal product. So we conclude that we conclude from here that an eigenvalue of zero mode of this case operator will equal to sum over alpha 1 over k sigma alpha and so on, sigma alpha plus k minus 1. So this eigenvalues are symmetric functions of sigma, and we can achieve any value choosing arbitrary sigmas. So in this way we can construct a fulfilled representation of this W algebra with arbitrary charge. And this is W algebra at charge at c equals n minus 1. But remember that when all the sigma alphas were 0, then this UK is commuted with J alpha beta 0. UK of Z. But in this case, the problem is that J alpha beta of Z is a series in non-integer powers. It is Z to sigma alpha minus sigma beta, sum of Jn alpha beta over Z n plus n plus 1. And these G's do not form a Cosmode algebra. So we can actually compute in the same way that if this is formulas for this GNs, so so it's not a smooth algebra. There are no zero modes for alpha different from beta. And but so in principle, these algebras are isomorphic, but these precise generators, which can be obtained from twisted fermions, do not satisfy these relations that we want. So we can look what happens with them. So this generators alpha beta of alpha beta and are the same as before. We can say that if you use some harmonic representations, and the diagonal generators, so there are these formulas. J alpha beta equals to psi star alpha psi beta. So if you use the same kind of reasoning, then we can find that like this one. We can find that J alpha alpha n equals to sigma alpha plus J alpha alpha sigma alpha delta n0. So if you now want to express, for example, commutators of these generators, so J alpha beta n J beta alpha minus n. So since off-diagonal matrices are the same as before, we can use the same permutation relations and say that it equals to J alpha alpha. So there is there is 1 plus no, so there is n plus J alpha alpha of J alpha alpha 0 odd minus J beta beta 0 odd. So if we now express them in terms of new generators, this gives n minus sigma alpha alpha plus sigma beta beta plus J alpha alpha 0 minus J beta beta 0. So see that it looks it looks like this indices of generators actually become half integer. So so another possible annotation would be to say that this is not Jn. It is J n minus sigma alpha plus sigma beta. So So it's this one is not a relation in cosmology algebra, but a relation in cosmology algebra with kind of shifted indices. Uh, so and and these operators do not commute with the double generators anymore for arbitrary sigma. So we could use them to construct this double algebra to check that it is actually some closed algebra because it commutes with something. And then we can deform this representation by introducing trivial twist. So they stop to commute, but the algebra is still closed. So in questions about this. So there's this example, and there is another example, uh, namely there's what is called twisted boson. So uh, and we can also notice that here this fermions psi star and psi had opposite monodromy. So if you multiply them, then a resulting object has a no monodromy, and so we can use it. We can use it freely. Mm. So it will be expanded in the integer powers of z, and will give the actual algebra that we want, like in W algebra or something, or something else. So how twisted boson? Maybe it is better to start from this application to entanglement entropy. So have you heard about this? Like about C over 3 logarithm of L? Ah, okay. So let me. Entanglement entropy in CFT. Ah, okay, so let me maybe start from this, as it is a kind of one of the applications of such constructions. So let us consider mm, some CP1, some sphere or plane. Well, let us say that this plane. Uh, I think. So let us consider a half plane and say that we are computing some partition function as a function of the values in the on the boundary of this half plane. So we have some so it is from minus I infinity to plus I infinity. Or maybe maybe it's better to rotate it. I don't know. It's better rotated. So maybe let us talk not about plane, but about complex sphere. It would be better. So we want to study some half of CP1. And compute, so there is this boundary. So D and dd. So I have a wave function. This is vacuum wave function because we don't put any operators here. So I have say vacuum is as a function of some bosonic field phi. So it is a path integral with d phi with phi phi on dd equals to the small phi e to minus s phi. So we have such vacuum wave function. And we can now say that that we want to consider some interval of size like from A to B. So this E is, since I is interval from A to B, and S1 is a union of I and complement to it. So we can say that Hilbert space L2 of S1 so no, it's not 2 of S1. So sorry, the Hilbert space now is so Hilbert space in our theory now becomes well, it is not very well defined. How to call this this tensor product because they are very infinite dimensional. But formally we can say that it is a tensor product of Hilbert spaces on the interval I and a Hilbert space of complement to this interval I bar. So this can be this means that psi vacuum and any wave function wave functional is a wave functional of a phi on I and a phi on I on complement of I. And so when we have this decomposition of the Hilbert space, it makes sense to consider a partial trace of projector. So by definition, density matrix ρ is by definition a trace of a trace over h I bar of psi vacuum times psi vacuum. So this density matrix, now let us write it explicitly. So this density matrix, so since it's an operator on the Hilbert space, then it has some kernel. So we have rho, which is a function of phi phi I and phi and some other function on the same interval, and it equals. So when we consider such tensor product, it means that we kind of add another hemisphere here with the same interval from A to B. And when we take trace, it means what? It means that we should multiply these two functions, actually function and conjugate, but here they are real, I think, and integrate over the values of field on the complement. So it equals to psi vacuum of phi I complement times psi vacuum of phi I tilde phi I complement. Oh, maybe we can add some star somewhere, but it's not important for the real field. And d phi I. So in practice, it means that we have a path integral. So there were these boundary values, and we now say that boundary values in one integral and in the other integral now coincide, and but boundary values on this boundaries from A to B are different. So we now need to integrate. So we now can write this integral as integral over the phi e to minus s of phi with the following boundary conditions, and that phi over let us call this interval I tilde. Phi on I equal to phi, and phi on I tilde equals to phi tilde. So the picture is the following. We have this sphere, and here we have a kind of slit. So um, the value of this field phi here. So we have one boundary and another boundary, I and I tilde. And there are different boundary conditions here. And so this is the operator of this form. And when you have this, when people have such object, they ask about the entropy related to this density matrix. So let me think. What is the correct sign? Plus or minus. Maybe minus. So yes, it is correct because for for r equals to 1, it should equal to 0, and for other rows, it is positive. So, yes, it is fine. Yeah, so, but we cannot, well, it is unclear how to compute this, so people say that we can use some trick, and namely to differentiate d over dn trace minus d over dn, a trace of rho to power n at n equals 1. So we first learn how to compute rho to the n, trace rho to the n, and get analytic formula, and then take this derivative. It's called a replica trick. Mm. So and if you compute such object, then it is clear what to do. We add. I'll draw this locally. So we consider n planes and say that if we come to this boundary, then we exit here. Uh, uh, we exit here, and if we go from this boundary, then we exit here, and so on. So it's kind of a ladder, um, and it is a Riemann surface of a function z z to n 1 minus z to n. So then we glue it here. So so trace rho to the n is a partition function computed on this this no this so it is an n-fold branched cover. And positions of these points are A and B, like y n's equals to z minus a, maybe b minus z, So when we are far away from these branches, then everything is fine. But when we approach it, we see local behavior like z equals y to the n, and different values of y parameterize different branches. So locally, we have I have this picture. So there's this branch cut, and so it is y of n equal proportional to z minus a. So there is a z plane here. So it is projects n to 1 onto the plane. The branch cut. So you can draw the same picture here. It is the plane. So since we are working with with a free boson, there is some field phi which lives on a cover. So here there is some phi, phi of some variable. In this case, we can write a global parameterization, of course, but let us just say that there is some field phi, and we can construct some fields below. And how to do this? If you choose some point on this plane below, then it has n preimages. I don't know which picture to use, maybe this one. So if you choose some point, it will have n preimages. So let me denote this field as phi tilde. So So if we want to construct something below, we can take the value of this field in any of its n preimages. So so this is a single field on covering a surface gives rise to n fields on z plane, and we can check the following thing. So we can ask what is the OP of this field, for example. So if phi I of z with phi j of w, it is what? So when these points are on the different sheets of this cover, maybe it's better to write here dz and dw. So when j is different from I, it means that pi minus I of z is so I is different from pi minus I of z j's, and so it is regular. But if I is equal to j, this equals to let us write it explicitly. So it equals to phi tilde of we need to take this preimage and preimage of this coordinate in the preimage is expressed in terms of coordinate in an image like z to 1 over n, 1 over n, dz to 1 over n, and phi tilde of z 1 over n dw of 1 over n. So and now we can say that this plane above is just the same it's just the same plane as below. It is just folded by this nth power. So OP of phi tilde can be computed as a OP above. No, sorry. I wanted to compute OP not of phi's but of j's. Sorry. J tilde. So this OP is computed as dz 1 over n dw 1 over n over z minus w. minus w to 1 over n squared. So here we have the same, we have a similar question, like how to expand this when z approaches w. And let me compute it in Mathematica. Mm. So the answer is the following. It is dz dw over z minus w squared plus n squared minus 1 over 12 n squared w squared. So it's fine. So if we expand this explicitly times dz plus regular. And this expression is actually a Schwarzschild of this change of variable z to 0 to 1 over n. But so we can check that this by differential transforms with addition of Schwarzschild. If we change z to f of z. But here we can just compute this explicitly. So well, maybe I can write, maybe I can compute this formula and write it. So the formula is that df of z df of w over f of z minus f of w squared is dz w over z minus w squared plus 1/6 f of primes over f prime w minus 3 third f, which is fraction. So we have this OP. We see that these bosons actually form the same algebra as n component boson. But we also see this correction to the regular part of the OP. So so now we can do the following. So now we can do the following. We define a T of z like this. It is 1/2 sum of maybe this index, this latent index is not very nice. So from 1 to n, j alpha of z, j alpha of z, normal product. This momentum tensor is invariant when we go around the branch point, because j alpha goes to j alpha plus 1 simultaneously. So like t of z is a single valued. And what is the central charge in this energy momentum tensor? Do you think? Yes. Hmm? Yes, yes. So from the point of view of this theory below, we have C equals n. And what we would like to compute the expectation value of this energy momentum tensor when z approaches a. So let us compute the expectation value of this energy momentum tensor when z goes to a. So from this computation, we know that each of these products, j alpha, had this asymptotics. So we see that it is sum from alpha from 1 to n, 1/2 n squared minus 1 over 12 n squared plus something like z minus a squared plus something regular. Regular oh, maybe not regular, but just less singular, less something. And the same for B. So it means that expectation. So it means that so we can compute this. It is n squared minus 1 over 24n 1 over z minus a squared plus and so on. So we conclude that from the point of view of theory below, there are some primary fields A, B. With delta n equals to n squared minus 1 over 24n. So we check this. And because of this, we identified these points as positions of primary fields. I can conclude immediately that this correlator, this one is actually a correlator of phi delta of A, phi delta of B. And we know the value of this correlator. It equals to 1 over A minus B to power. So if we include also anti-homomorphic part, it will be absolute value of A minus B to 4 delta n. And if we denote the limits of this integral L, then it equals to L to minus 4 delta n equals to L to n squared minus 1 over 6n. So this is a trace of maybe we can write its computation in the theory above. It is a trace of rho to power n equals to this. Now remember the definition of entropy. So then S equals to what? Minus d over dn L to sorry, 1 minus n squared because of the opposite sign. L to 1 minus n, 1 plus n over 6n. So if you differentiate these terms, it will vanish when n goes to 1. So we should differentiate this term, and it gives 1 plus n over 6n logarithm of L plus all of n minus 1. And then when n equals to 1, it gives 1/3 logarithm of L. So and in general, if we consider a CFT with arbitrary central charge, of course it will appear here. So S will be equal to C over 3 log of L. Let me think. Oh, in principle, it can be proportional to some maybe it depends on normalization. Also, in principle, this needs some normalization because, for example, logarithm of the dimensional quantity is not very well defined, but at least qualitative behavior can be seen here. And the origin of this central charge here is also clear because we can say that T of Z can be written as a sum of T tilde of like dz squared T of Z can be obtained as T tilde of prime images I d v minus 1 of Z I squared plus sum of Schwarzschild. Plus C over 12. And if we take this z to 1 over n map, it will precisely produce the same term, but with the central charge here. Do you have any questions about this? Concerning normalization of this entanglement entropy, like why should this function be why should two-point function be 1? It is easy because when n equals to 1, we get just a trace of rho, and so trace of rho should equal to 1. So there is no no extra factors. So the first version is this one. Yeah, I want to tell another related story. So we studied this at this field for arbitrary n, and now we can consider a special value n equals to 2. So it will not be related to this entanglement entropy anymore, but it is related to another interesting story about exact conformal blocks. So when n equals to 2, we can say that there is there is some field above, and so there is some j and tilde which is of z, which is z, which is sum over a n over z n plus so we can construct another field below, which is g of z dz, which is j tilde of z to 1 over n. Maybe it's better to use some different variable here. W dz to 1 over n. To 1 half. So this field, it's more expansion in this one. It is 1 half sum of an over z n n plus 1 over n over 2 plus 1 and dz. So it is sum over integer and half integer modes. And we can decompose this field into the sum of two. So we can say that it is sum over n into z, or maybe, well, over integers a to n over z to n plus 1 dz. And plus sum over half integers again 1/2 a to n over z n plus 1 dz. So this is with an integer indices form also form a Heisenberg algebra, because commutator of a to n with a to m equals to n delta n plus m 0. So we can say that this is equal to some other bosons. So we can say that a to n is equal to some Cn multiplied by square root of 2. So that we have this commutation relation. So commutation relation was Cn Cm is delta n plus m zero times n. And the same can be done with this half integer a's. So we can say that a, but here it will be tricky. So in commutation relation of 2k plus 1 with a to n plus 1 and to m plus 1 equals to n plus 1 delta n plus 1/2 m plus 1/2 plus m plus 1/2 0. So if we introduce the field B in the same way, so B P will be 1 over square root of 2 A to B. So then commutation relations of this B with itself will be like B with B minus B will equal to 2P for half integer P's. So working on this whole together, we see that it is this current is a sum of 1 over square root of 2 Cn over Zn plus 1 dz plus so for integer z and some over half integer z's. Well, we can say that this current is big G of z, and this we will call I of z. Oh, sorry, not n plus 1 half, but n plus 1. So now let us try to construct an energy momentum tensor of this theory. So as before, we say that it is 1/2. Actually, let us say that only this part is I of z, 1 over square root of 2. So let us say that it is I, and this is I of z, and this is j of z. So here we take some over plus plus and minus. So it is j of pi. So it's an epsilon which equals plus minus j of pi epsilon of pi inverse of z epsilon. So in other words, it is 1/2 sum of so 1/4 j of z plus I of z for one frame image plus 1/4 j of z minus I of z because it changes sign when we change the frame image 1/4. So in total it gives 1/2 j normal order plus plus 1/2 I. And if we now look at the formula for the value of for the expectation value of the energy momentum tensor, we can avoid this boring computation with modes of I. We just see what is written here. So we can say that when we compute this regular product, it is 1/2 j squared plus 1/2 of I squared plus this value, like 2 squared minus 1 over 24 times 2 to z squared. So it equals to 1/2 of g squared plus 1/2 of I squared plus 1 over 16 z squared. So I've used that formula for n equals to 2. So we can now look at this and say that this term is, we can call it t plus of z, and this we can call t minus of z. And since this odd and even parts of boson commuted, these are commute universals. And so the consequence is that this is also Virasor. And what do you think? What are the central charge of this? But hmm? Oh, but originally we had only two-fold cover, so it was c equals to 1. And they then decomposed it into a sum of two Virasors. One Virasor is just a free boson without any defects, so it is 1. So remaining central charge should be also 1. So, right. So the consequence in that those generators form so there is this representation of the Virasor algebra. So when n is different from 0, this L is equal to sum of 1/2 of some over half integer p's a p a bn bp and bn minus p. And for L0 we have a different formula. It is 1 over 16 plus a sum that plus 1/2. Maybe uh, So. mm, so it is a bit similar to what happens with Cosmology algebra. When we try to check Virasor relations between L and M's that do not involve this L0, then everything works as usual. Even when we commute L0 with other L's, it just computes in the degree, because this 1 over 16 commutes with everything. And so the only difference appears when we try to compute commutator of ln and l minus n, and Virasor relations tell us that we should get the L0 plus central extension, and what we get is this expression 1 over 16 plus this operator. So uh, the vacuum vector for such a realization of Virasor has dimension 1 over 16, and it is different 1 over 16 than we saw in the Ising model. It appears in a bit similar way, but it's different, because in that case it was a degenerate field, but in this case this is a dimension. This is a dimension of general position. So there is no there are no vectors in the Varma module, and mm, then I want to tell about computation about an exact computation of conformal blocks of such fields with dimensions 1 over 16. And actually, so if you compare this this Fock module of this mm, half integer boson, it actually contains uh, infinitely many Virasor modules. So we can see this in the following way. So maybe I can raise in this computation. So I want to compute the expression which is sum of q to two deltas over the over all of all highest vectors in this Varma modules. So we can compute the trace of q to L0 using the fact that this is this is boson, and that L0 counts the total dimension of this bosons plus 1 over 16. So it can be written as q to 1 over 16 product of 1 minus q to the power n product of k equals to 0 to infinity 1 minus q to k plus 1 half so forgot a little bit how to do this, but probably we can do like this. We can add a sum over all half integer numbers and add corresponding counterpart to the numerator. No. Oh, no. Do the opposite. And in the numerator, we write 1 minus q to n over 2, 1 plus q to n over 2. So to 1 over 16. Oh, sorry. So we need to do we need to derive this identity. So we can write product 1 minus q to the n is 1 minus q to n over 2, 1 plus q to n over 2. And then we again can separate this into even powers of n and odd powers of n. So it is a product 1 minus q to the n, product of 1 plus 1 minus q to the n plus 1 half uh, product of 1 plus q to the n, product of 1 plus q to n plus 1 half. So then we cancel on this left hand side and right hand side, and say that so we have this. So so there is this identity, and now we should remember that there is a Jacobi identity, which says that it says that some over integer numbers of some t to n, q to n squared over 2 equals to 1 minus q to the n, product of 1 plus q to the n plus 1 half t, 1 plus q to the n plus 1 half t inverse. Wait. Actually, I forgot this computation. So this sum should be expressed as some theta function, but and it also has some physical interpretation of in terms of performance, but I forgot how to do this precisely. So I need to remember this, and probably I'll tell this next time. Mm. And by the way, concerning the next time, so is it okay if we meet after the New Year, like on 9th of January? So,
Yes.
uh, will be because on this Thursday I will have two lectures on equations of mathematical physics. Oh, technically it is possible, but in 6 hours of lectures maybe it's not too much. Mhm.
Okay, so next lecture is on 9th of January.
Yes, and then on Thursday on the same week.
Yeah.
Only two. Yes. So do you have any questions about this?
I think just
Mhm. Okay, so thanks for your attention.